Okay. So last time also I told you that there is a reading assignment, only this one. A lot of things I'm using in the class is from one of the references. It's a very famous reference for wave propagation, Achenbach. And then there is another optional reference if you are more interested, and this is here. But this is a reading assignment. That means that there may be questions referring to the material in this paper in homework or in the exam. So please take time to read it. So what I hope to cover on surface waves is, first of all, why they exist, how they are different from body waves. Are you familiar with the expression body waves? What do you understand under body waves? When I say body waves, what do I mean? What do I mean when I say body waves? Yes, the waves that travel within the body of the material, which is basically P and S. There are other kinds of waves too, but we normally mean P and S waves. And then we talk about surface wave testing, how it works, why it is attractive, and what do we get out of it. So for those of you who took the candidacy exam, this picture looks very familiar. And you have seen it also before. We are looking at three different waves. So the second and third ones are the ones you know. Does someone want to explain the difference between the second and third? You all are now experts better than me. The second in the middle, what type of wave it is?
The second is P wave. We can see that there's an arrow inside. It is actually the way the particle moves. We can see that it is perpendicular to the propagation direction.
This is perpendicular to the...
Sorry, I want to say it's parallel.
Okay, so this is the wave propagation, right? We see the direction up there. And this is the material when it doesn't go through anything. So you see all the cubes are cubes. And here we see that some of the elements are compressed. Some of them are kind of, how do we say, stretched. Yes, they're stretched. So this is this kind of movement you have learned about. Thanks, Andrew. So how about here? This we have also talked about. This is a S wave. This is now polarized in this direction, so we call it, the particle displacement is, we can see it is up and down. So what did we call it under S wave? SH or SV? SV. SV. SH is when it is, don't worry, I mean, it's a convention, it's not a problem. So this is SV, don't worry if you didn't write it in candidacy exam, I haven't taken points off. I can see like people getting nervous, no. It is fine. So now what we want to talk about today is the one on the top. Pay attention to the shape of these elements. So this is undisturbed material. And here is how it is distorted. The difference between here and here is that the elements change lengths, but here they change angle. They are not perpendicular to each other anymore. This is a distortional wave. This is a dilatational wave. I could pronounce this word. Dilatation, that's great. So that's the main difference. How about here? Both. We have both. So pay attention, at the bottom, we don't see much is happening. Everything seems to be happening on the top, and then you have both. The elements are distorted as well as dilated and compressed, stretched. So this is Rayleigh surface wave. Why I put word Rayleigh here? Because there are other types of surface waves. Anyone has any ideas about other surface waves?
No.
Log waves. So there is a wave which is also propagating along the surface but has this kind of motion. It's going in this direction. And that's log wave. We won't talk about that, but just that you know there are other types of waves. This is not the only one. So, oh, and the particle motion. It is not one-dimensional anymore, it's two-dimensional. You all said that we have kind of both displacements, and it's kind of going opposite to the direction of propagation. It's what is it called? A retrograde ellipse. So this is kind of a qualitative understanding of it. This you have seen also before, but we need to take a little bit closer look here. When you have an impact on the surface, you have all bunch of waves. You are generating a lot of different waves. So here, for example, it's just kind of a point load. We want to see what type of waves we are generating. Let's look at compressional waves. This is P wave. Why do we call it P wave? Primary, because it comes first. So as you can see here, the thickness that you see represents the amplitude. So we can see that the amplitude is maximum just below the location of the loading. Shear wave has a much more complicated pattern. So this is a spherical, or in this case semi-spherical wavefront, and see how shear wave is kind of maximum around here, and actually in the middle is 0. Okay. Now, this we have seen before, and also you see these powers, they show the geometric spreading. I've shown you this also before. Now, what we want to look are these two components. So here we are also creating surface Rayleigh waves, or Rayleigh surface waves, Rayleigh waves going along the surface. And what you see here is how the motion changes with depth. So you can see that, for example, here the vertical component is maximum at some distance, at some depth, and then it goes very, very fast towards 0. And the horizontal component has a completely different behavior with depth. Another point is, look here, in terms of the energy, if you calculate how much of the energy, what's the percentage is being carried by which waves, Rayleigh waves have a very large portion, 67%.
Can you explain that again? Percent of total energy?
So when you wave propagation is basically the traveling of energy, a spreading of energy. So you can calculate what is the percentage of energy being transmitted by Rayleigh waves, or S waves, or P waves.
So this is the percentage of the initial that's emitted?
Right, so this is, if you sum them up, hopefully you get 100.
I see. Oh, okay, so this
so
is
we
the
have
distribution
100,
of
exactly.
Okay.
So that's the percentage of each one of them. And we see that Rayleigh wave has actually a large portion. Do you know why is that? Up to now we are just talking about body waves, and all of a sudden I come and say, this is very important, it's carrying a lot of energy. Why is that? Let's look at this figure. With reference to this figure, why do you think is this happening?
Closest to the source?
They propagate. So they all start here, and then Pay attention to this.
Does it come back?
That's the geometric spreading for Rayleigh wave because it has a cylindrical waveform. It's not a spherical.
The geometric.
So what do you see? Yes, Tiffany, sorry. Yeah.
Is it the geometric spreading is less because it's cylindrical?
What does it mean?
What's attenuation? What's attenuation?
So let's say, what exactly does it mean? Does it mean that if I have some sort of a trace like that, how do you think we would recognize Rayleigh wave here? It's on the surface. I measure a trace like that on the surface. The amplitude. Rayleigh waves they don't attenuate that fast, as Mahbube pointed out, right? They attenuate very slowly. So at the same location, P wave and S wave have been attenuated a lot, but Rayleigh wave is still very large. So it's very easy to pick them. The hardest thing to pick is S wave. P wave is the first arrival. Rayleigh wave on the surface is very large. What is hard is S wave because in terms of velocity, it is somewhere in between, and there is no like particular feature associated with it. So it's kind of hard. So this is another way to represent the same figure now with color, so you can kind of see how the amplitudes are. Those red you see close to the surface are Rayleigh waves. Okay, now with all this introduction and saying that how great it is, let's see how we can describe them. I mean, the wave equation that we were playing with so far doesn't explain Rayleigh waves. It was within a medium only for body waves, right? We had velocity of shear and compression of wave and nothing about Rayleigh waves. So we have to kind of find out how to get there. So let's first talk about why this is called Rayleigh. Any ideas? So it turns out that a guy called Lord Rayleigh in 1887, he basically understood that near the surface we have motion which remains near the surface, and whenever we have a free surface we have these kinds of waves. So that's where the name is coming from. And how does it work? So the first thing to understand is that Rayleigh waves are confined to the region near the surface. So this is x1, this is x2. We just talk about very simple case, two-dimensional plane wave. What is the direction of propagation? X1 or X2? X1, right? No, these are my policies to make like equation derivation fun, to kind of distract you, ask you questions like that. So let's call the velocity C sub r. R for Rayleigh. What happened? R for Rayleigh, and I'll explain later on why C and not V, but some people also use V sub r, it's fine. So we are considering the 2D, so basically U3, I assume that there is no motion perpendicular to the plane. So Lord Rayleigh, he said that, this motion is confined to the area near the surface. So we assume that the displacements decrease exponentially with depth. Okay. If you were to write the equation of a wave propagating in x1 direction and attenuating exponentially in x2 direction, how would that look like? Do you want to give it a shot? General equation of a wave propagating in the x1 direction using wave number and velocity. So velocity is CR, wave number is K. How does it look like? Write it down. I just want you to see that you know all of this right now. So the equation right? So one is omega t, one is kx. This is the very general equation of a wave propagating in the positive x direction with velocity cr. You agree? Everyone agrees about that? Positive? If this is confusing you, k times cr is omega, right? So we have omega t, we have kx, and this is the essential equation of a wave. Now I'm saying it has to attenuate exponentially with depth. Do you want to add a term, an exponential term, which shows that? Exponentially attenuating with depth. So we have some amplitude. I've used A for here. Mahbube, you said something. Yeah, minus x2 times some attenuation coefficient. That's exactly it. So I want you not to be afraid of equations. We have it. This is a very general formulation for a wave propagating in the x direction with velocity c sub r attenuating exponentially with depth. Agree, Ingjun? So how about U2? The same thing. It's just that since it's the same wave, we assume that it's basically the same way it's attenuating, and it's propagating also in the same direction. So, but it has a different amplitude. Now, for this to attenuate, really to attenuate with depth, what condition should I put on B? B has to be positive, right? Otherwise, it's not going to happen. So, more generally, the real portion of B has to be positive, so that U1 and U2 decrease with depth. And for now, we have assumed that U3 is 0, so we don't have to deal with this. Okay, great. So we have this, and we already know wave equation, general wave equations where there is no boundary conditions, nothing. I hope you remember some of that. Like in 3D, we wrote it down as something like that. it's just really an extension of one-dimensional, where E is the volumetric strain. Remember anything like that? So, and then we had also for torsional wave an equation like that. We defined some torsional strain. So we are not going to go through derivation, but basically all we want to do is to make sure that U1 and U2 satisfy wave equations. So if we plug U1, U2, and U3 into wave equation, we are going to get this expression if we don't want to have non-trivial answer. When I say trivial, it means that everything is 0, right? It's clear. So this is the expression Vp squared. Vp is the velocity of compressional wave. B is that factor e to the power of minus b x2. K is the wave number. V sub s is the velocity of shear waves. B again, we talked about. It's actually a beautiful symmetric equation. So, from this we can solve for B1 and B2. We get two roots for B1 and B2. And B1 is K minus CR squared VP squared. This is a square root. And B2 we had this condition that B1 and B2 have to be positive. And they are real and positive when so if we just substitute it and impose that B1 and B2 should be positive, we immediately see that this is only possible if the velocity of this wave is smaller than the velocity of shear wave. So that's the first thing. And that's what I want everyone to remember, that Rayleigh waves are traveling slower than shear waves. Questions?
So the equation that you wrote, you have to solve for CR.
No, so far what we did was this. We kind of started with the concept that Rayleigh started. He said, okay, there is some wave near the surface, but it is really near the surface, so it attenuates fast if you move from the surface. Okay. So this is the general expression for a wave traveling, and this makes it to be confined to the near surface region. So we just take that. I'm not really showing how, saying that we plug that into wave equation. We plug that to the wave equation, and we get this. If we want to have non-trivial answer, that means if we want an answer where A and B are not both 0. A trivial answer is 0 is equal to 0. But if we say that no A and B cannot be together equal to 0, normally you have to say that a determinant is 0, and then that's the expression you get. And now, for all of this to make sense, B1 and B2 have to be positive, because otherwise, what we have started with doesn't make any sense. If this is negative, it's going to grow with that, right? So, if we impose that, we get this expression. If we impose that, we see that this is only possible. You can see here. It's only possible if CR is less than BS or less than BP. I talked about I haven't written what is what, but I kind of assume that we all know, and I said it verbally, that VP is the velocity of compression of air, VS is the velocity of shear wave. Right. So if you, please write down in your notes, I didn't write it down here explicitly, but
right now I was just asking, so Rayleigh waves are the slowest?
yes.
Even though they have the highest
amplitude.
Right.
Yeah. We'll talk about the amplitude, we are just building it up.
Okay.
So this is why you already knew, but this is how we get to the fact that this cannot be bigger than any of that. Otherwise, this will become, this is imaginary, and then it's not going to go exponentially decreasing, right? It is a square root. 1/2 is a square root. So if that's larger than 1, an imaginary number comes out, and then when you have imaginary number and E, it's oscillatory, right? It's not going exponentially down. So that's where we are coming from. I skipped a lot of steps because it will be too long otherwise. Yeah.
What is the equation at the top from?
Okay. We plug U1, U2, U3 into wave equation, and we ensure that we are looking for a non-trivial answer. That means not A and B can be at the same time 0. So you know how to calculate, you have even all the expressions to do that, and you are more than welcome to try it. So if you look at the lectures in wave propagation, when we derive this, we have expression for all the stresses, for all the strains, and how to calculate this. Now, I'm giving you U1 and U2. From U1 and U2, you can calculate a strain. You are still linear elastic. You can calculate a stress. You can put it here. And if you do that, and ensure that we are looking for a non-trivial answer, that means not A and B equal to 0, which is an obvious answer, right? Then we get into this equation. I have skipped all of that, right? I'll be happy to show you all the derivations. This is something I really like, but I don't think this would be a good use of our time. But if you want, I can always show you. And you can look at the reference I gave you. I'm not sure if all the derivations are there, but it's possible to do it. There is another way to get to here using complex integrals. I wasn't sure how many of you know about that, so I chose the easier one. Yeah, right. Yeah, complex integrals are very useful, but we don't want to, go into the details. At the same time, I want you to understand where things are coming from. Not just, this is a smaller than that, so what? Now, we are not done in any ways. Now we have this B1 and B2 that we got from here, and they result into some expressions for, remember B and A, these are the amplitudes I gave in the beginning to U1 and U2. So corresponding to this B1 and B2, we also get these two expressions for the ratio of B to A. Oh, because this equation is in terms of b squared. So whatever you get is b squared, so you have plus minus kind of. You get several roots. It's not only one. Now, if we use this b over a, let me write it. So substitute for b over a in expressions for u1 and u2. I should say that this is a big change. In the beginning of the semester, I remember no one wanted to look at the equations, etc. And now you ask questions about them. So this is kind of encouraging. I have conveyed some of that love of mathematics. Okay. So now if we plug in for a, we don't have explicitly a and b, but we have their ratio. If we put that back in u1 and u2, this is what we are going to get. This becomes now more and more interesting conceptually. So it becomes like, so the first pair, it will be like b1, a1, and the second one b2, a2. So we can get two components, and then we can say that, okay, the general solution is a combination of two. Okay, and then you see that the b over a and b over a, that now they play a role. So u2 is I'm just using the same ratios that I have above, basically multiply it by a2 to get b2. So this is basically b1, and this is basically b2. You see? And then we have b2x2 These are components of the same weight, so traveling with the same distance, and this is how they look like. No, it's not velocity. We used it for displacement, right? I should have said that in the beginning. And we use u for displacement, and this is the displacement in the direction x1, and u2 is the. So maybe you want to, just for the sake of completeness, just put it here that it becomes clear. It's like particle displacement, just like what we had for P and S. Yeah, it's been a long time. I should have explained this a little more. Okay, now we have nice expressions for U1 and U2. No, if you look at these two, what do you see? Okay, it's a hard thing to say, but this is not the right question. Is there anything in particular that you see in relation of U1 and U2? And to give a hint, what do these eyes do here? So one is like A1, A2, and nice. It's like two components of what we had before. And this one, the amplitudes are multiplied by an imaginary number, like I. What does that tell us about U1 and U2? What do you mean by that?
Orthogonal.
Yes. They are 90 degrees out of phase. That's exactly what it is. So U1 and U2 are, you have the same wave, but the two components are 90 degrees out of phase. But this was great. Thank you. So U1 and U2, that's the first observation. And you look at it and you know exactly why, right? It is like, when we went from displacement to velocity, when you add I omega, whenever you have one I, you have a 90 degrees rotation. That's what it is. Okay, great. Now, so far, we didn't even impose any boundary conditions. This is surface wave. So far we were just following what Lord Rayleigh told us to do, that this is confined to the near surface region. We haven't imposed any boundary conditions. What did we start saying? This is a surface wave. That means for it to exist, we need a surface, right? So what would be the boundary condition? And we also don't know what A1 is, they're still open. And to get that, we need to impose the boundary conditions. So what are the boundary conditions you think we should maybe I just write it down here, but you may change to the, what's the boundary condition? It's good to try. Okay, it's good to try. At T0, U1 and U2 are the same. I mean, do we have a reason to do that? Does it have anything to do with the surface? I think what we haven't done, we haven't imposed is the fact that, this is going to travel along the surface. What do we know about the surface? In a bar, what did we say about the endpoints? Right. So here it's like a 2D. So the stresses, we have a 2D situation. The stress on the surface has to be 0. We haven't imposed that. This is surface wave. So if we do that, so we would say that at free surface, stresses are 0. This is two-dimensional, so if we translate it to free surface means x2 equal to 0, right? This is what we have. And since we have U1 and U2, we can calculate epsilons, and we can calculate epsilon, I mean a strain. We can calculate the stresses, right? You know these expressions, you have it in your notes. And if we do that, we are going to get these two equations. This is really imposing the boundary condition. It's 2. I'm sorry. 2. I kept these equations here actually so that kind of we review when we say what does it mean not to have trivial answers. So this is an equation, you can think about it is to solve A1 and A2, correct? So for having non-trivial answer, that means when A1 and A2 are both 0, this is trivial. If we don't want that, we have to make sure that the determinant, if you look at this as a matrix equation, the determinant is 0. You know what I'm talking about, right? Yes?
Are you intentionally to put 2 times B2 times A2 divided by B2?
Where are we talking?
The second equation?
2 times B2, A2 over B2. I think so.
So
I don't know this by heart. I don't know if it is.
you don't want to figure out.
I don't know. Maybe it's a typo. I can look at it, but I don't know the equations by heart. But maybe it's just written such that we have them both in the same form. I check it. I check to make sure that it's not a typo. Thanks for pointing it out. But I don't know. Let's look at the next equation to see if it's hard to say, but I can take a look to make sure that this is correct. What is important is what comes next. So for this not to have trivial answer, it means that this determinant, which should be this times that minus this, should be 0. And that's where the other equation also comes from, very similar. And then we get to this very famous equation for surface wave velocity. And this is here. Let me write it down in the next page. This is correct for sure. Yeah. Okay. Trying to see if the other equation is correct or not, but you have to substitute for B1 and B2 too. It's fine. This is a very famous equation because there is no closed form solution for the velocity of Rayleigh wave. This is what there is. It expresses the velocity of surface waves in terms of shear wave velocity and compressional wave velocity. There are a few observations to make. One is that it is only a function of the other two velocities. Wave number came out of this equation. We don't see it, right? So we want to write down that, one observation is that the wave velocity, CR, is independent of wave number K, and depends only on basically VP and VS. What does it mean when I say it's independent of wave number? What's the implication? So if a velocity is not frequency dependent, it means it is, what is the word? If a velocity is frequency dependent, what do we call this phenomenon? No. Velocity. We are talking about velocity, not attenuation. No. I mean, velocity, we know that p wave velocity and s wave velocity, everything is dynamic, but no. But we know that they are just a function of material properties. This is in the context of surface wave testing, as I will tell you in a few more minutes. It's very, very important concept. What do we call the phenomenon of the dependence of velocity on frequency? Dispersion. Dispersion is the word. So what it tells us here is that if we have only a half space, an elastic half space, the other way of expressing this is that Rayleigh wave is non-dispersive in an elastic half space. I write down this sentence because it's important. So that's the implication. Rayleigh wave is non-dispersive, and later on you will see that it is dispersive in some other circumstances, and that makes Rayleigh wave very interesting. It's non-dispersive in an elastic half a space. And then add a little note for yourself saying, explain what non-dispersive means. That means its velocity is not frequency dependent. So what I'm writing right there is independent of wave number. This is what it means. Okay, but this equation is kind of hard, and you know, it's hard to, question?
Oh, no, sorry.
It's a hard equation to deal with every day. So there is an approximation. So this is an approximate solution, which is basically, we need to memorize it. That's Poisson's ratio. So 0.862 plus 1.14 Poisson's ratio over 1 plus Poisson's ratio times V sub s. And of course you can see that it could be like that because we can express this in terms of Vp and Vs or Vs and Poisson's ratio. Now you know all of that. And this is good for this Poisson's ratio, and it gives us some limits. So it is between 0.955 and 0.862. The ratio of wave velocity, the Rayleigh wave velocity to shear wave velocity. So you can see that it's slightly slower than shear wave. And here also there is a table which you can see for different values of Poisson's ratio what these look like. Okay, this is about the velocity. So, yes. And it's a function of the P-wave velocity and shear. So if you look at the approximate expression, we see that it's written in terms of shear wave velocity and Poisson's ratio. Right. I think that somewhere I also have the expression with P-wave. I do. I'll show you to you. But this is what we have. So far this is about the velocity. Now we know what is the velocity of P wave, S wave. Now also you know what's the velocity of surface wave.
So what do we ever done with the top ratio for or not?
I have organized it such that first we talk about the theory and application, but exactly the same way that you use the velocity of shear waves, for example. You can, if you measure surface wave velocity, kind of Poisson's ratio is always constant, or it doesn't vary much. So we can estimate shear wave velocity. That's most of the time what it is being used for. Now you may question why not measure shear wave velocity.
And then the top equation.
So I mean, the top equation you can solve it numerically. There is no closed form solution for that.
Right, so then just use
So this is a solution, an approximate solution to this equation.
right, so that's what I'm saying, we're not going to use the top one.
No, but it's a beautiful equation and a very famous one, and you just have to know about it. I mean, it's very symmetric and beautiful. I mean, it's amazing that you get an equation like that. Also, you can solve it on everything. Yeah, this is kind of an approximate solution to that. There is no like, you know how in P wave we immediately got a square root of m over rho or f wave? It just doesn't happen here with the boundary conditions and what we have. And this is what we have. Now how we use this, we'll talk about it, but it's the wave velocity. The nice thing about surface wave is that the source and transducers are all on the surface, and you measure directly the wave velocities. That's the nice thing about them. And since they have very large amplitude, it's easy to find them, to calculate the arrival times, etc. So they're actually pretty nice. And this dispersion is very important, and that's what we are going to develop into the applications. But first, we need to talk a little bit more about the displacement, because they're also very unique in the way the displacement works, right? From the beginning, we said the displacement is confined to the top part. Okay, let's focus on this one first. What are we looking at? The curve number 1 is U2. That's displacement perpendicular to the surface, like that, normalized by U2 at the surface. That's why it's 1 on the surface. So the y-axis is x2 over lambda. Lambda be the wavelengths. And curve number 2, as you may guess, is u1 over u2. It's the displacement which is parallel to the propagation. And you know that they are 90 degrees out of phase. And what we want to look here is how they change with depth. Take a moment and make some observations here. What do we see? So this is 0. Okay, these are the axes. And I've rotated the figures, so we have really x1 in the direction of the wave, and we have x2 in the thickness direction. Let's make some observations about this figure. What do we see? What are some things we can write about this figure? It's extremely important. This is like the most important thing about surfacing. Yeah. This is a good observation. U2, that means the component which is perpendicular to the surface is larger than the component which is horizontal. So for this reason, a lot of times people actually don't really measure the other component. They use geoforms in one direction, I mean almost always actually. So they kind of only focus on one component, U2. Very good. So one observation is that U2 is is larger than u1. I mean, remember these are 90 degrees out of phase, so this is very loosely written, but it's larger. And on the surface, for example, you see that u2 is 1, and u2 is 1 compared to 0.6. So on the surface, it's about 1.5 times larger. And that's where we measure it. What else? This was great. Sheng, you are quiet today. Yes, good observation. So u1 at about 0.2 times, this is like x2 over lambda. So here it's changing direction. This doesn't have much practical implications in what we will talk later, but it's an important point. u1 changes direction at x2 about 0.2 times lambda. Yes. I'm sorry.
They actually right next to the
Oh, this is normalized by u2 at x2 over 0. That's what it means.
like this number and this 1 and this 2.
That's just the name of the curves.
Oh,
One
okay.
and- yeah. I don't know why it's reversed, but I explained from the beginning what each curve is. So curve number 2 is u1 over u2 at x2 equal to 0. I don't know why there is this opposite number. And this curve is u2 over u2 x2. You have the expressions. You can actually plot this for different Poisson's ratio if you like. There is one very, very important observation missing. Higher frequency, but this. What do you
said I don't know, this graph is showing.
This is just normalized by x2 over lambda. So what we have is basically a multiplication of lambda. It's in the right direction, but
it's like when it goes to the depth of like 1.5 or 1.6 depth of lambda, both directions, both u1 and u2 will contribute.
this is exactly it. This is the main important observation. If you look, what's happening when you go towards depth, if you are even 1.6 times lambda, the amplitude is small. Actually, practically, you don't have any amplitudes beyond 1 lambda. Mahbuba, I'm not sure I understood the point you were making. Let me write this down and we talk about that. So I write it this way. I wrote a nice sentence before that the motion is basically pretty much confined to a layer of thickness so about, let's say, 1 to 1.5 lambda. 1 lambda. I mean, it becomes very small. This is what it is showing. So this is depth. Yeah, we can see, right? This is 0. This is 0, right? This is approaching 0. And here, this is already 0. And that's extremely. So this is the most important thing you have to know about surface space. That the motion is pretty much So think about it this way, that the wave is traveling on the surface. Okay? You are measuring it on the surface. However, it's affecting 1 lambda of the material. And whatever you are measuring is affected by the properties of the material 1 lambda underneath. You can imagine that this is very attractive to any kind of subsurface characterization, whether it is non-destructive evaluation or it is geophysics. Yes, it is. And that's exactly great. Yeah? Mm-hmm. Yes, so velocity and wavelengths, they have, this is 2 different things. This means, let me make it very clear. You have the same material. The velocity is the same. If you use a higher frequency, I think this is pretty much what Mahbubeh was, if I'm not mistaken. That she was also the point, she was going ahead of us a little bit. And if we have the same material, okay, if you use a source which is higher frequency, that means that the wavelength is smaller. That means that if the surface wave is propagating, it's propagating with the same velocity. However, it's affected by a thin layer. Versus if you use a very high, low frequency, the wavelength is larger. What you are measuring, it comes from a thicker layer. If the material is a half a space means you have a space of elastic, homogeneous, isotropic material, and you cut it in half. So everything stays the same. The velocity should not change whether you are considering this much or this much, right? However, this becomes very attractive if you have layering in your system. Then you can actually modulate the frequency to penetrate into different layers. And this is when I say applications, that's what people do, especially in pavement testing, because it's perfect, right? You have a layer system, or geophysics, the same way. You have a layer system, so if you have a range of frequencies, you can probe different layers just being on the surface. You don't have to have anything else. You're just on the surface, and you are measuring everything on the surface, but you are getting information from deep down. And that's the beauty of surface waves. I mean, it's what this is. No, go ahead.
Is there any significance about the 2 curves meeting each other, or just showing that?
They're not really meeting each other, so they're 90 degrees out of phase. So this only shows that how they're changing the thickness. They're not. They're kind of 2 different components. Here, important is to see that U2 is much larger, and then that they vanish very soon. So they're going like that. Like they're kind of going opposite to the way they're traveling. And this is how it goes there. And here are the stresses. I've rotated. There was a question.
And U1, U2 are amplitude of the particle.
Right.
So what is that?
I'm sorry.
Why U1 is that amplitude of
It's just the other direction. It changes direction.
the particle moves like this.
Right. So instead of going up, goes down, or instead of going right, goes left. It shows the direction. Direction, the positive direction, this is all relative to what I showed you in the beginning. The positive direction is this. If you are moving in this direction, it's negative. The positive direction is this. If you go upward, it's negative. Understand? You even see that in the motion, you go up and down. So that is.
Yeah, so the direction is changing.
It's not a scalar, so you can have direction, right?
The particle moves like this.
Right.
So
It changes with depth, as you can see. This is not like P wave or S wave. It changes with depth, as you can see. So at every depth, you have to look to see what is U1, what is U2, and how the particle, we have pointed out as a second observation, at point 2 lambda, it reverses, U2 reverses. It's a complex motion, and it depends on the thickness. The main difference between surface wave and body waves is that the motion depends on the thickness. And that's the kind of a beauty of it. That's the whole thing. So here is basically we are looking at the stresses. So this is displacement. And here we are looking at the stresses. The namings, again, these curves are strange, so I write it down. It's also written here if you rotate your head 90 degrees. I put it this way so we can kind of visualize it better with x1, x2. So curve number 1 is sigma 12 over sigma 11. It's also normalized. Curve number 2 is sigma 22 over sigma 11. As you can see, they both are 0. This is what we required for this to be. And 1 is sigma 11. We don't use this much. I mean, displacement is what we use, but right. Yeah. So let's.
Does that mean that that's time zero and then it's just
No, it's that means surface.
okay.
Everything is
Maybe it's at the surface.
right. So look
Okay.
here. x2 equal to 0 is here. This has nothing to do with time. This is at every time.
Okay.
At every time.
Okay, that's the condition you're ready for?
Yeah. Because it's always on the surface. We cannot have.
So when we're saying the displacement, we're saying like how whatever we're doing at the surface. is
No matter
affecting
what
different
time,
particles at different depths.
Right.
And
Right.
okay.
Right. Exactly. So when we are saying that the stress is 0 on the surface, it's always.
Right.
It doesn't matter what time we are looking at. So. Okay. It's a good place to stop. So you see, it's a very important topic.